Okay. Right. So we left off where we were talking about one's complements and uh, how we can use them in subtraction, how they are used in manipulation of arithmetic processes, specifically subtraction. I give an example. We subtracted 7 from 24 using the human way, borrowing, which, by the way, you probably won't see in the exam. So, no much worry. You just need to know for the sake of learning. But the ones complements, probably you see those. All right. So we calculated this one using ones complements. We gave uh, the process for calculating using one's complement, and we said steps number one, you take the second operand and you find the one's complement. Second operand, find one's complement. The second step, we said add binary numbers. The third step, add the carry to the result. Right. Now, there is a case where you're trying to find the difference of two numbers and you get a negative number. How does computers deal with that? Here, 24 minus 7 is positive 17. No problem. But what if you want to subtract 24 from 17? We know this is a negative 17, but how does the computer do it? Actually, doing this, I'm actually thinking, why do we even need to know how does the computer calculate? Why not just calculate? Then that's it. I'm hoping all you engineers have the answer for that. Why? Why? I'm just like thinking, why are we even doing this? But here we are. We are trying to find the difference between 7 and 24. All right, this is how we do it. You follow steps number 1, number 2, number 3. They are 7, this is 111, 24, 0, 0. 24 is 1, 1, 0, 0, 0. Step number 1, take the second operand, find the first complement. In this case, this becomes our second operand, 24. We find the ones complement is 0, 0, 1, 1, 1. Step number 2, add the two numbers. When we add these, we get 0, carry 1. This is 1, 1 plus 1 plus 1, 1 carry 1. 1 carry 1, 1, 0. There is no carry there. So it means step number 3 is invalid. Step number 3, we cannot use step number 3 in this case. This is the solution we get. But is that a negative 17? Is that a negative 17? Yes. But not to us humans. To us humans, that is not a negative 17. To the computer, that is a negative 17 because that number is in one's complement. That is the 17 using one's complement. Negative 17 is one's complement. For us humans to understand that, If I take the first complement of this number, it gives me complement. It gives me 10001. What is this number? It is 17. But as humans, we know if I subtract one big number from a smaller one, I always get a negative number. So I know when I get this 17, it is a 17 with a negative. Computers don't know that. What computers know is the complement. So the solution for the computer is this one, which is negative 17, which is the complement of this. If we complement, we get this. Computer shows you this. So there's a bit of complication when identifying the results of the difference between two numbers. If the operand is smaller than the other one, I'm not sure what's the name of it. For example, here, 7 is smaller. It means you get a positive number. There is no need of changing, of complementing and all that stuff. There is no need. You just follow the 3 steps. If the second number is bigger, in this case, 7 minus 24, there is need of identifying the result you get after step 2 or step 3 in other cases as the ones complement of the original result we know as humans. So this is a negative 17. Solution here is 1, 0, 1, 1, 1, 0. Base 2. This is a negative 17. Yeah. Right. And that's it for one's complements. Practice makes perfect. Trust me, I practiced this example to the extent that I can tell you. You also need to practice for your exam. Otherwise, I don't feel about number. Believe me. All right, we go to the 2's complement. How do we subtract using the 2's complement? How do we subtract using the 2's complement? Let's use can we use the same example? Let's use another example. Let's use another example. All right, we are going to subtract 25 from 14. 25 minus 14, 25. What is 25 as a binary number? Participation. Right. Did I get my participants here? What is 25? And what is, I said 25 minus 14. What is 25 and what is 14?
1 1.
It's 1 1 0 0 0 1.
Okay, and what is 14?
14 is
0 1.
0 1. Go on.
1 1
0
1
1
0.
1
1
1
All
0.
right, start again, 1 person at a time. 0 1
1
1
1
1 0.
1 1 0. Is this a 14? 8. All right, this is a 14. Thank you very much. Father MTMI and who else? Who else? Angarutara. Identify yourself.
Mbizai.
Rumbizai. Gwinji. Okay. All right. These two numbers represent our binary numbers, 25 and 14. How do we subtract them using the 2's complement? All right, rules. Step number 1. Step number 1. Step number 1. take 2's complement of the second operand. 2's complement of second operand. Step number 1. Step number 2, add binary numbers. Add binary numbers. Step number 3, discard. Discard the carry. In 1's complement, we added the carry to the result. In this case, we discard. Right. Now, how do we go about this? Step number 1, 25 minus 14. Step number 1, 2's complement of the second operand. Second operand here is 14. This is 0, 1, 1, 1, 0. How do we find the 2's complement of that number? Step number 1, when finding the 2's are equivalent of that number, invert. Step number 1, we invert 1, 0, 0, 0, 1. Step number 2, we add 1. We add a 1. So this is 0, carry 1, 1, 0, 0, 1. So this is the 2's complement of 14. 2's complement of 14. 1, 1, 1. Is this correct? Yes, it is correct. But let me do this. Let me represent, excuse me, let me represent these two numbers using BCD representation. BCD representation, let me see. I'll do this. BCD, which means we have the same thing. It means we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. This is our 25. This is our 14. You need to get used to doing this. It's a crime representing numbers like this, the way we just did, using 5 numbers. We don't have a number system which is like this. I think you understand as we move on with the course that the number systems which we will be using are BCD and all those others. They don't represent numbers like this. You have to replace using another 2, 3 zeros here, so that you have 8 bits. Right. Mute yourselves, or you get removed. All right. So I was talking of representation of binary numbers. You cannot represent binary numbers using 5 bits. You can, but I advise you, for the sake of learning, it's either you represent using 4 bits, or Frederick, mute yourself. You're very fortunate I cannot find you here. All right. Okay. I think I found this one. Excuse me. We continue. Avoid using representing binary numbers using 5 digits. You can use 4. You can use 8. I advise you to use 4 and 8, which means if you want to represent a 3, instead of doing this 1, 0, 0, this is a 3. Okay, true, but it's better to represent it like this. If you want to represent a 10, I can do this 8, 4, 2. This is a 10, fair and fine, but it's better if you represent it like this. 1, 2, 3, 4, 5. 1, 2, 3. I hope I got the point across. That's why I had to change here. Right. Now that I've changed, let's continue. 1, 0, 16, 24, 25. Right. Right. We go and continue with our calculation. First step, second complement of the second operand. Second operand here is 0, 0, 0. Another 0. That is not correct. Is this a 14? 8, 12, 14. It is correct. 1, 1, 1, 0. That's a 14. The second complement of that number, we invert first. 1, 1, 1, 1, 0, 0, 0, 1. After we invert, we add 1. 0, 1, 0, 0, 1, 2, 3, 4. This is the 2's complement of the second operand. Right. After you find the 2's complement of the second operand, you move on to add the 2 numbers. So we are now adding these 2 numbers. Right. So we have 0, 0, 0, 1, 1, 0, 0, 1. Are we still there? Feedback.
Yeah, terrible.
Right. Plus 1, we're adding with this one. 1, 1, 2, 3, 4, 0, 0, 0, 0, 1, 0. What happened there? 1, 2, 3, 1, 1, 0, 0, 1. 1, 2, 3, 1, 1. And this one, 1, 2, 3, 4, 0, 0, 1, 0. Representation angle is a bit all over the place. That's why I'm getting all over confused. Right, so this is 1, 2, 3, 4. 1, 2, 3, 4. Now we add the 2 numbers. We get 1, 1, 0, 1, 0, 0. Okay, this is 0 carry 1. 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 This is the sum of the 2 numbers. We are done with step number 2. We go on to step number 3, discard. Step number 3, discard the carry. So we remove this. We are left with this value. What is this value in binary? This value in binary is 8, 4, 2, 1, 8, 10, 11. What is 25 minus 14? 25 minus 14 is equals to 11. So it means my complements edu are ushanda zvakanakisisa. Right, we go on to second example. Going to the second example. Russell, faites attention. Be very careful. All right, the second one, we have a case where we know we are going to find a negative number. We know we are going to find a negative number. How do we then calculate? You follow the same steps. Step number 1, choose complement. Step number 2, add. Step number 3, if necessary, remove the carry. And lastly, step number 4. For the case of negative solution, if the second operand is bigger than the first. Right. If the second operand is larger, the result is in 2's complement. If the second operand, it means the result you find after adding the 2 numbers is already in the 2's complement. In the case where the second operand is smaller, the result is binary normal. binary normal. For that other one, the result is already in the 2's complement. I think the first complement we already did, we find out the same thing. We found out the same thing, that the solution, if the second operand is greater than the first one, is in its complement. Right. To test the theory, whatever that is, we have 14 minus 25. What is 14? 14 is 0, 0, 0, 0, 1, 1, 1, 0. What is 25? 25 is 0, 0, 0, 1, 1, 0, 0, 1, 16. Right. This is 25. First step, take the second operand of the second complement of the second operand. So we invert this one, 1, 1, 1, 0, 0, 1, 1, 0. We add 1, 1, 1, 1, 0, 0, 1, 1, 1. We add this. So we have 1, 1, 1, 0, 0, 1, 2, 3. Addition 1. 1 plus 1, 0, carry 1. 1, carry 1, 0, carry 1, 1, 1, 1, 1. This solution, because the second operand is larger than the first, it means this solution is already in complement form. The solution is already in complement form. Now, if we take, how do you then find in human form what is the value there? In a digital system, this is a negative 11. This is a negative 11. But how do you verify it? It's a negative 11. It's also negative 11. Tinoziva 11 akadaiso. 11 is 8, 4, no, 2, 1. This is 11 ish. Right? We want to find out, can we link this negative 11 in 2's complement to the negative 11? We know. So we have, let me see, the negative 11 we found, it's, it's 1, 2, 3, 4, 0, 1, 0, 1. 1, 2, 3, 4, 0, 1, 0, 1. The 11 we know it's 0, 0, 0, 0, 8, 4, 2, 1. Right. If we find this is the 2's complement, 2's complement. Process of finding the 2's complement, you invert number 1. Number 2, you add 1. Process of going vice versa. Number 1, you subtract the 1. Is it correct? 0, 0, 0, 0, 1, 0, 1, 0. We subtract the 1. What is the 2's complement of this? Now let me see. 0, 0, 0, 0. Just a minute. 1, 0, 1, 0. Right. This is wrong. We subtract the 1 from this one. Unfortunately for this one, I'm doing a lot of calculations in my head. Let me get the result, then I come back to 1 minus 1, 0. Then we have 0, 1, 0, 1, 1, 1, 1. Then the complement 0, 0, 0, 0, 1, 0, 1, 1. It's the same, right? Right. Correct. Let me go back here. I said the result when we subtract a larger second operand from the first, the result, this one, is already in 2's complements. Computers understand this is a negative 11, but I need you as humans to also understand this is a negative 11. How do you understand that? If you want to go from a normal binary number to a 2's complement, the process is complement. The process is 1, you invert. 2, you add 1. So if we want to go from the 2's complement to a normal binary number, you go vice versa. The vice versa way, it means 1, you subtract a 1, then 2, you invert. So we subtract a 1 from this 2's complement number. That is what I was doing. So we subtract a 1 here, we get 0, 0, 1, 0, 1, 2, 3, 4. Then we invert, we get 0, 0, 0, 0, 1, 0, 1, 1. This number is the same as this one, which is an 11 normal number. Unfortunately, for humans, we cannot see if it's a negative or if it's a positive. We know because 14 minus a bigger number, 25, we know it's a negative number. I'm trying to find out a way if we can identify it from using the sign bit magnitude. If there is a 0 here, it means it's a negative. Let me see the other one. Sign bit magnitude representation. If there's a 0 on the MSB, it means it's a negative number. Let me find out if there is a positive, if there is a 1 on the other one. 14 minus 25. This is 24 minus 14. All right, there was a 1, but we removed it. Here we are. Watch. This solution we got here. There was a 1 here, but we removed it. And that 1 from the sign bit magnitude representation, it means this is a positive number. I'm just trying to link the 2's complement representation, even the 1's complement representation, and the first type of representation we did, which is the signed bit magnitude representation. That's it for 2's complements and 1's complement. It's important to understand the treatment of the sign bit for 1's and 2's complement codes. Why? Because that is where the arithmetics of digital numbers is entirely based. All right. That's it for complements. Complements 1 and 2. To summarize what we did today, we introduced signed numbers. Signed numbers, by signed we mean positive and negative. We added those numbers, we subtracted, we multiplied. With subtraction, we mentioned there are some complications when we do subtraction. That's why there is need for complements. Complements are there to simplify subtraction in digital systems. We showed each other how do we use complements. Nope. Number 1, how do you convert a normal binary number to a complement? How do you find the complement of a normal binary number? 1's complement and 2's complement. That's the first thing we did. Then we applied that knowledge of finding the complements to subtracting, finding the difference between 2 numbers. And I think basically that's it. And for today, I think we are done. We have 7 minutes for questions and comments. You have the floor. Unmute yourselves. I think I'll have to mute myself. Okay. And it seems we don't have any questions.
Hey.
We don't. Okay, so
Okay.
Moana, introduce yourself first.
Okay, my name is Tariro Soswana,
Tariro.
HCE, Computer Engineering.
Okay, question.
Ndinobvunza kuti zvonizvo last time pamakati zvonizvo tiende noresearcha muma-compliments paingobuda zvemabinary chete. Does it mean kuti zvonizvo ma-compliments anoapply kuma-binaries chete apply kuma-octal nema-hexa what?
I think they do, but you have to go via binary. If you have an octal number, you want to find the complement and all the other stuff, you have to go through the binary system. I think the computer can do that because you know the conversion of octal to binary, right? So it means if you give your computer an octal number and you want to find the complement of that number, it first converts to binary, then find its complement. I think to sum it up, I can say I have no knowledge of direct manipulation of octal's number system to find the complements. I also only know of binary. So I think it's octal, binary, then complement. Everything passes through the binary system.
All right, so thank you.
Any other questions? 5 minutes. Nope. And I think that's it. Thursday. Thursday mambo wearing. Thursday mambo wearing. We meet Thursday. If I'm in a very, very, very working mood. But I think I've put out a lot of information there. Practice, compliments, and everything. I'll probably give you Thursday for that. And I think that's it. Thank you for attending the session. Thank you for participation. Have a good afternoon.